consider on the number line, because when you have asymptotes, you have to look on both sides of them. And so this could be an asymptote we have to look on both sides. Now we put our critical numbers on a number line. So here's 0, that's just an asymptote that we have, and then here 5.419. And this breaks up our number line, doesn't it? Splits us up. And I can throw out the left side of 0, right? I can throw this out. Why? That's not even our domain, right? So we don't need to look over there. Now what am I going to do? Take a number in here, plug in 1. Plug that 1 in where?
To the derivative. We figure out what it's doing.
Derivative? It's derivative.
We figure out what it's doing, and then we can plug and see what that point.
All right, I want someone to explain why it is that it gets plugged into the derivative. Don't tell me because I told you. Like,
it's going negative, positive, or positive, negative, or negative, positive.
okay, good. So the derivative is what tells you about where the function is going up and down. So when you plug this number into the derivative, if it's positive, that means the function is going up. If it's negative, it goes down. So if you're ever confused as to like what this goes into, just remember what would happen if you did plug this in to the original function. If you plugged 1 in here, all that would give you is the y value of the function, right? Or the y coordinate of that point. That's it. That doesn't tell you if it's going up or down. That just tells you where you are. All right, so what happens if I plug 1 into this? You're going to get what? 4 pi take away 2,000 over 1? That's negative, isn't it? That means my original function is going down here. I could say A if I want. A, the surface area function, is decreasing there.
It's negative 1,900.
And then I pick another number over here.
6.
6. Could I pick 10? Sure. 100? Sure. Whatever I want. It's bigger than this. And then plug it in here. You have to do 6 cubed and then times 4 pi and then subtract from 2,000. If you do that, I'm going to let you do it on your own. Trust me, it's going to come out to be a positive number. Right? So that means that our function is going up here. And 5.419 was a critical number, right? This number is in the domain of the function. So we have a local minimum here. How do I know that that's the global minimum? What's that? Yeah, there's no other place. Look, if there was a place on this graph that was lower than this one, this graph would have to come back down and then turn back up. But it only goes down between here and here, and then from here on, it just keeps going up forever. So it's impossible for it to have a lowest point somewhere else. So this is it. This is the one.
But if it had, let's say, if it was a different equation, it had multiple, then we'd have to figure out which one.
Then you would have to see which one of those was the smallest. Would give you the smallest area. Yep. But fortunately for us, it only happened one time. So it's obvious that that's our candidate. So now I'm going to just kind of write this down. We have a local minimum at, I always ask you to write it as a point, right? So it'd be 5.419. And what did I say to do with that 5.419? Plug it into the original function, right?
Which is 553.5.
What do you get?
553.58.
553 point what? 58. All right. I think we're ready to draw a conclusion here. Everyone see that we're kind of done? We just need to wrap it all up. All right. What was the original problem asking us? Find the dimensions of the can which give us the smallest volume. It never even asked us for the smallest volume, did it? I mean, not smallest volume, smallest area. It never asked us for it. But in my answer, I'm going to give this person everything I've got. I'm going to give them the dimensions and I'm going to give them the area because I want them to know how intelligent we were, that we were able to recover all this information. Okay, so here we go. The smallest area possible.
Surface area.
Okay. I thought it was implied, but I will correct it. Smallest surface area possible is what? And we're approximating things here because we're using decimals, right? What is the smallest area? That's right, it's this number right here, because remember, what we did is we plugged in R in this this was going into the A function, right? So this was R being plugged in, it was spitting out A. So it's going to be 553.58, what? Centimeters squared, because it's area. Good. Smallest surface area possible is that. The dimensions must be the following. We know what R has to be, right? R has to be 5.419 centimeters. But there's another dimension I need. The height.
So we can plug that.
So go back into your work and look at your constraint equation. Your constraint equation is where you solve for R, right? And if you go back in there, it was R was 2,000, no, it was,
1,000.
sorry, H was 1,000 over pi r squared. That was our constraint, right? So I can solve for H if I know what R is. I do know what R is. So you plug R into this, get on your calculator, and it says 10.840-ish centimeters. And that's it. That's the smallest area possible, and that's how it needs to happen. Go tell the people who are going to make the machines to build a can. That's what we need. Now I think I did say when we first visited this problem, when we were just talking about it way back in the beginning of this chapter, I said that it turns out that if you build a can, that the optimum way to do it is so that, does anyone remember what not? No?
It was the radius is equal to the height.
Close.
Or double the height.
Close. That the diameter and the height must be the same. That's what I said. It turns out if you're going to build a perfect can, perfect minimum surface area, the diameter needs to be equal to the height, which is the same as saying that the radius is half the height. I don't know if someone said that. I didn't hear that. Did he say? Okay. The radius must be half the height.
Kind of like a square.
Yeah, it's kind of like a square. Like if you looked at this from the side, the can from the side, oh, that's terrible. I don't know if that looks like a square to you. But this distance of the can must be the same as this distance of the can. If you build it that way, then it's going to give you the least amount of surface area. Now, we did not prove that, okay? We didn't prove that. To do that problem, you would have to do this problem in general, which means you would never fix V to be 1,000. You would just leave V as V throughout the entire problem. And the algebra in that is very ugly, and it's not something I'm going to do in here. But it could be shown. And what you wind up at the end is that basically this R winds up being half of H. What I wanted to point out to you is that I can confirm it by just asking you to look at this right here. If you double this radius, that's diameter, right? And that's equal to the height. So these two follow what I said would happen. All right. What do y'all think? Any opinions?
Kind of like the same section from last one, except between the shapes into it.
Yeah, I mean, you see why this is application. We're applying what we've learned about how to find max and mins to functions, but now with like real world applications. Like this could be used by a company. All right. I did graph it, but here's the solution we got right there. That's the lowest point on that graph, and 5.419 for the radius, 10.839 for the height. Volume, of course, was 1,000, and then the surface area, 533. Yes?
Just kind of a curiosity question, but are the soda cans you get like in the store and stuff, is that how they, is that?
No, do you remember why we talked, did we not talk about why they don't do that?
It's something that has to do all with pressure.
It's not a perfect cylinder, right? Like if you look at it, it's got the divot in the bottom, and then like I think the thickness of the aluminum on the top and bottom are different. And then, yeah, for the expansion they have like that, like almost like a hemisphere, like a semicircle on the bottom. If it gets too much pressure, that pops out. So there's a lot of other factors that have to come into play. And then there's also like the aesthetics, right? Like, you know, Monster Energy is not going to build this little wimpy looking can that, you know, it's got to, I'm sure they sit people down in a room and say, like, which of these cans looks the meanest to you? You know what I'm saying? Like there's a lot of things that go into it. It's true. I mean, it's true. But I mean, on a purist, from a purist point of view, if you want to save money, then you're going to do that. And I believe that if you look back in like the 50s, when you would buy like oil for your car, like for your engine, the 50s and the 60s, when you go to the store and buy oil, the old oil cans had like, remember how you open, have you ever seen like a can opener where it just punches a hole in it? Those cans used to be made using this, or real close to it.
Otherwise, you used to have the pull tab cans. They were the same way. They were just really cylindrical. And just pull the tab on.
Yeah. So I don't know. I mean, when you manufacture a can like that, the lid is manufactured separately from the outside and it's pressed on. So there's other factors, but this is just like the equation we use for objects falling on Earth. We take the wind out first, right? And then later on, or take the air out, and then later we add the air. If you're really the monster company, which is really like what, Pepsi or something, whoever it is, Coke or whoever, then you have, hopefully you've hired some people who are going to think through this and are going to go, look, we need to take it into consideration. This. Come up. They probably have some function that gives you the area of their can, given all these different constraints. Their constraints are different than the one we had. It's more than just the 12 ounces that they need. They need a lot of other things. So I don't know if that answers your question, but yeah. And I think that a lot of it is the aesthetics, you know, like Red Bull. We all know what the dimensions of a Red Bull can look like, right? Like Red Bull, it's a certain kind of, you know, they like to be different. And I think that plays a lot into it, you know. They're willing to spend more money on the material if they can make something that's going to stick in people's minds. Yep, question? Red Bull size? Yes. Okay. I can't speak to that. Yeah, not on camera, I can't. Am I even recording? I am recording. Okay. Oh man. Okay, this next problem, let's see, we got about 25 minutes. All right, yeah, I'm going to let you look at this first and just think about it. Although you were supposed to watch a video on it. Find the point on this graph, which is a parabola. So there's this parabola here. Find the point on this graph, which is closest to the point 3,1. When I think of a problem like this, and I'm like, why in the world would we ever need to know something like that? Is when you think about like the paths of meteors and things like that going through space, and you've got little Earth sitting here. And these things that are traveling out in space are not traveling in straight lines. There's a lot of forces acting on them. And so they have paths that are sometimes parabolic, sometimes elliptical. And so if you have an idea of what the path is, you can figure out, like, you've heard this, right? Like, this meteor is going to be like this close to the Earth, right? Like, how are they just kind of going, man, yeah, it looks like it's about that far away. You know, I mean, you know what I'm saying? Like, they're not just guessing at it. They're using a model. They kind of know what the path is, and they know where we are, and they're trying to find the minimum distance between us and that path. That's exactly what we're doing here. Wow, where do we even begin? I mean, you have to make sure you understand what's being asked. So is anyone ready to write down what we want yet?
We want to know what's the closest point to that point.
What's the closest point to that point?
Like, where on that graph is that come closest to?
Okay. Can you phrase that question and let me force you to use either the word maximum or minimum? So rephrase your question, but you have to use the word maximum or minimum. Find the minimum distance between 2 points, right? I mean, that's basically what this is coming down to. You want to find the smallest distance between 2 points. One of them isn't changing. The other one can be anywhere on here. Do you see that? So I like that. Let's start with that. We might have to tweak it a little bit, but I think that's a good place to start. We want the minimum distance. How do you say that? Minimum distance between, did you say 2 points? I like that. Is everyone on board with that? Well, if you need the minimum distance between 2 points, you're going to then need a distance function, right? You need a distance function then. So we need a distance function. And this is the point at which I like to start to draw pictures. We already had the picture, didn't we? You have to keep in mind here, we're kind of cheating a little bit because when I present these to you in the notes, I give you the picture, right? But on the book problems in the homework sections, this is it. That's all you're going to see. Find the point on the graph, blah, 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 which is close to this point. So you don't have the picture to go off of. So one thing you could do is, spend some time graphing it. Go to Wolfram Alpha, graph it. But I claim we don't need any of it, right? I don't need any of it. I can do it all without a picture. So we want the minimum distance between 2 points, so we need a distance function. You ready for a distance function? What is the distance? Do we have a way of figuring out the distance between 2 points? Slope gives us the rate of change between 2 points, but we can use the same picture. Let's use the same picture for the slope. If somebody gave us, so this is kind of a recall from sometime in the past. Someone asked you to find the distance between 2 points x1, y1 and x2, y2. And you want to find that distance, which we will call d. We could construct the right triangle. See, this again goes back to the whole idea of the difference between knowing something and understanding, or like memorizing something and understanding it. Some of you are good memorizers, I'm not. So you could have the distance formula memorized, great. But I think it's more constructive if you can actually develop it on your own just from looking at some of the geometry behind it. So what is, this distance is the hypotenuse of this right triangle that I just created. And I can figure out the length of these two sides if I know these 2 points, right? If I know the x and y coordinates. So what is the distance from here to here? Other way. Good. y2 minus y1. This is the difference in your y coordinates. And this distance from here to here is the difference between your x coordinates, right? And then Pythagorean, a squared plus b squared equals c squared, allows us to create the relationship we need. X minus 2, x2 minus x1 squared plus y2 minus y1 squared must equal d squared. And I want what d is, right? Not d squared. So I take the square root on both sides. So I have this. D is equal to the square root of x squared minus, I said x squared, x2 minus x1 squared plus y2 minus y1 squared. Now, does that look familiar? Okay, that was at some point hopefully given to you, and I wonder if I don't even know if the formula sheet, does it? It's on here, okay? So it's on the first reference page, the distance formula. But that's where it comes from. So we've got it, right? Now, is there anything in the problem that we're doing, is there anything that we can definitely, not rule out, but we're trying to find the minimum distance between 2 points. One of them is along a path of a curve, right? And the other one is always the same point, right? So within our formula, one of these, either the x1, y1, or the x2, y2, is always the same thing, right? So why don't I use my distance formula, and let's just say for us, x1, y1 is going to be the point that we were given in the problem, which was 3, 1. So in my distance formula, I can replace this right here with 3 and this right here with 1. Okay, great. What about the other point? It's not fixed, is it? It's changing. But there's something you can tell me about it. x2, y2. What can you tell me about it? I actually need the equation, so I'm going to have to write it up here. Remember, you had the parabola. The other point lives on this parabola, right? It was y squared equals, was it 4x minus 1? Okay. That was the parabola that your other point lived on. Can anybody help me? Tell me about this point. You can't fix anything. Hold on. Can't fix. You're not allowed to fix any points at all.
I'm saying there's gonna be two. I don't know.
Let me try and help you with a totally different example. Let me just show you something. Okay, this is a side thought over here. This comes up quite a bit, so I want to make sure you all understand it. If I wrote down this equation, y equals x squared, let's say plus 1. If I wrote that down right here, and I asked you to graph it, we would all draw a parabola that opens up, and it's moved up 1, right? We would do this. If I came over here and I told you plug in 1, it would spit out 2, right? Yes? Plug in 1, it's going to spit out 2. But if I told you to plug in x, what would it spit out? 1 plus x squared, right? 1 plus x squared? Yes? So look, the ordered pair here that we have is the input here is x, isn't it? What's the output? X squared plus 1. Y'all follow me? So coming back to this idea of this parabola, can you tell me about this point right here? If I plug in, let's say x here, what comes out? The square root of 4x minus 1. See, you would have to solve this for y. Solve this for y, you would get plus or minus square root of 4x minus 1, wouldn't you? So if someone gives you x, it spits out the y. Now it's going to spit out 2 y's. Why is that going to be?
So because it's now irrational?
It's opening sideways, right? So this parabola is not a function of x. Fails the vertical line test. All we're concerned about is the upper one, the one on top, because our point is above the x-axis. There's some subtleties in this problem that I understand are a little confusing, but Stop me if you need clarification. Are we all right on this? All right, so what is that y coordinate going to be? Positive square root of 4x minus 1.
Why is it not going to be the negative part?
That would, the positive one of these draws the top, the negative one draws the bottom. Our point is here, right? I think it's safe to say that the closest point on this graph has nothing to do with the bottom piece, right? Now that would require that you have some idea of what this looks like, right? There is another way you could do this. It's a little, I actually haven't even considered working it this way, but if you didn't like that this was not a function of x, you could, all right? You could at this point solve this for x. Just hear me out. This would be y squared plus 1 equals 4x. Agreed? Divide by 4, so you could have, I'll write it this way, 1/4 y squared plus 1/4 equals x. You could do this. And now, this ordered pair over here, I could do backwards. In other words, if somebody provides me a y value, what's the x that gets spit out? 1/4 y squared plus 1/4. I could do this problem either way. I could do it either way. I'm going to stick to the first way, though. All right? I know this is kind of a little bit of a stretch. Yes?
Sorry, off topic. Why do we need to have a vertical line test if you can have a function in either direction? You can have after this, after that, or by this.
Why do we need to have a vertical line test? A vertical line test is a quick way of checking whether or not one function depends on the other. That there's that mapping that only goes this can only go to one place. It cannot split off into two. Right? Now, I need to get to your question because I think what you're asking is why do we even have a test? This right here would fail the vertical line test. What does the vertical line test tell us? Whether or not this is a function of x, right? So when you fail the vertical line test, it's not a function of x. That doesn't mean that it couldn't possibly be a function of y. And what do you think you need to do to see if it's a function of y? You actually do the horizontal line test. So this would be a function of y, but not a function of x. And if you draw a circle, it's not a function of x or y. And see, I think I understand where you're coming from because it's kind of like, well, I don't know if I understand where you're coming from. What I can say is that this frustrated a lot of mathematicians for a long time. This whole idea of function of x, function of y, and it fails. We want to work with circles, right? We want these to be functions. We want them to, but they fail all our tests. So we actually have a workaround. And that's what parametric equations are. That's what when you can define a function parametrically, which you would see that later on, okay? And then you can draw curves and they still qualify as functions, but they can do some crazy, and I won't use my normal language in here because we have a guest, but you can draw some crazy stuff and that's still a function. It's just we got to define it, and make sure. Yeah. So I don't know if I'm getting to your point,
No,
but
I was confusing the vertical line test, with it being just a function.
the vertical line test only tests if it's a function of x.
Yeah.
That's all it does.
What you're referencing to, I guess.
Yeah. It's limited, but you got to think also when you learned it, like that was like, okay, that's a quick, easy way to check if it's a function, So like back then it was like, yay, but now it's kind of like, well, all right, It's there. All right, we are 9 minutes, and I think what's going to wind up happening here is I'm going to set it up and you're going to go home and do it. All right, so we have what our x1, y1 is, we have what our x2, y2 is. And we're trying to find the minimum distance between two points. We have a formula that gives us the distance between 2 points, and we wrote it down, and now I'm going to rewrite it. D was equal to the square root. It was x2 minus x1, that quantity squared. What is x2 here for us? X minus 3, so that's going to be that quantity squared plus, y2, square root of 4 minus x, or 4x minus 1, that's y2, minus 1, that quantity squared. Okay. I've lost my spot. Wanted the minimum distance between 2 points, so we need a distance function. Is our distance a function of a single variable? Yes, it is. So good, we don't have really a constraint, or do we? The constraint is the parabola itself.
The constraint is it being close to that.
It has to be on the parabola, right? That's our constraint. That is the constraint. It's inherently there. So I'm going to rewrite this as d of x, just to let everyone know, hey, I've got a function of x. And I want to know when this thing is the smallest or biggest it can be. The smallest, right? That's my distance function. After we come up with the function, what is it that we needed next? Domain. What's the domain of that function? Ooh, crikey.
Because x is greater than 2, it's going to be,
Good. This is the only piece of the problem that we have to consider right here. Is the fact that right there, we need to make sure that's never negative.
Don't we have to also make sure the whole thing is greater than or equal?
Yeah, so why am I not considering that? Because look, this is a big root, right? That's a big root.
squared.
And I'm taking the square root of something, I should look at what's underneath it and consider whether or not it's negative. But the fact that this square root, think of the picture it comes from. This square root represents the distance between 2 points, right? And I know that the distance between those 2 points will always be positive because one point lives off that parabola, the other point lives on the parabola. And so I know that this radicand can never be 0. There's no way it's going to happen, as long as I didn't mess up the formula. I had to make the formula correctly. But I know that the radicand of this is fine. The only consideration is that this piece right here could possibly be a negative number. So let's just make sure that 4x minus 1 is always bigger than or equal to 0. Oh, this is domain I'm talking about. Domain. And so the domain of this, just solve this linear inequality. X must be greater or equal to 1/4.
Why isn't 3?
Pardon?
Why not 3?
Because this right here, this expression doesn't have a square root in it. This one does. So I need to make sure that what's underneath this, the radicand here, I need to make sure it's not negative. This right here can never be negative unless what? X is 3? Well, sorry, did I just say negative? I don't think I meant. This can never be negative because it's squared. Do you agree?
Yeah.
The worst it could be is 0. And then we're adding to it this over here, which is also squared, so this could never be negative. The worst it could be is what? 0. Put those two together, there's no way we could have negative under there. But this root by itself, that could happen, right? Let me, look, just try it. If I plug in -2 right now, what happens? -2, that gives me a negative under here. Can't do it. So there is a restriction on my x. And because we cheated, and we actually looked at the graph, can you see from this graph that my parabola does not exist to the left of 1/4? Right? So if you're on this parabola, your x-coordinate must be bigger than 1/4 or equal to 1/4. But we can see that from the algebra. We don't need the picture to see that. All right, man, I'm kind of at a point where I need more time because we have a domain, right? We have a domain for this function. We're going to be looking from 1/4 and then forever. There's no upper restriction on x because as long as this thing is satisfied, this distance is defined. So I keep going forever. You looking forward to taking the derivative of that and setting it equal to 0? No. Okay, so I think because we only have 2 minutes.
What if we use the power rule that?
Oh, you would have to do lots of chain in here. This would be chain with some more chain.
What about more logarithmic differentiation without?
Logarithmic might, you drop the 1/2. Now you have a sum in there, so it would be a problem. So I think I have enough time to at least motivate the idea of where we go from here. We could take that derivative, right? We're not afraid of it. We could take that derivative. But it's really that big square root on the outside that really we don't like. We don't like any of this stuff, but there's a standard protocol that we use in problems like this. All right, there's a standard protocol. Basically we squared, but I'm not going to present it to you that way. That's really what we do. Like what winds up it winds up looking like that. It winds up looking like that, but it's not that. Okay? So I just wanted you to consider something before I give you the next thing in 2 minutes. If I asked you right now to show me the square root function, y equals root x, just root x. We all know that root x looks like this. Your standard square root function is always increasing. Increasing. Increasing means as I read it from left to right, it's going up, right? Always. So would you agree that if I plug a point in, I get a y value, that in order for me to get a lower point on the graph, I need to plug in something smaller, right? And that would give me a lower point. And if I go something smaller, it's going to be even lower.
It's the thing you did last time.
It's the
Newton's theorem, right?
No. I'm sure. I'm sure that's what I'm not trying to get. That's not what I'm trying to get you to see. All I'm trying to get you to see is that on the square root function, because it is always increasing, as you move to the left, your points come down. So if you want smaller values, you just move to the left, right? Yes? Okay. So if I have the square root of some junk, okay, which is what I've got here, the square root of some junk, the smaller values, right, the smallest values I'm going to get out of this thing are going to require me to make that radicand small. The smaller I can make the radicand, the smaller I'll make the root. Does that make sense? It only works because it's an increasing function. That's the only reason it works. The reason I'm telling you not to just square it and make the radical go away is because this will not work in general in any function. You can't just go square it and then take the derivative and follow the same process. You might lose your maximums and minimums if you do that. It's dangerous. So instead, I'm relying on the fact that the square root function is increasing, and because it's increasing, if I can minimize the radicand, it's equivalent to minimizing the function. You're gonna, what? I'll say it again. Say it again.
Oh, create a ratio?
No. Do you want me to say what I said again?
Yeah, go ahead.
Okay. So from this picture, to make this graph smaller, I have to make the x smaller, right? Equivalently, to make the square root of some junk smaller, right, I need to make the junk smaller. So when I look at this problem, all I really need to focus on is trying to make the radicand as small as I can. So this problem is about to transform into a new problem. It's going to look like this. I need the minimum of some new function. I'm going to call it r of x. R is going to stand for radicand. Okay, it's the radicand of this thing. And this is what I'm going to send you home with as a take-home quiz. We need 2 quiz grades, right? So here's one. There you go. And let me just double check something on here. All I want you to do on this problem is take its derivative, clean it up, set it equal to 0, and you're going to get, when you do that, a polynomial function equal to 0. Y'all with me? Yeah? That's your take-home quiz. I want you to write down the polynomial equal to 0. If you want an additional 3 points added on to your last test grade, you're going to take that polynomial and you're going to, it's set equal to 0, you're going to solve it using Newton's method because it can't be solved by hand. When you do this, you're going to take the derivative of this. Vector. You're going to take derivative of this, right? Figure out what it is, clean it up, it's going to be something. You're going to set it equal to 0. When you do that, you should get a polynomial equal to 0. This polynomial cannot be factored. You can't use synthetic division. There's no way you're going to be able to solve it other than Newton's method or just going to Wolfram Alpha and asking for the answer. But if you show me Newton's method on it, it only takes 3 iterations of Newton's method.
Oh, that's all.
That's it, 3 iterations. But your starting point has to be picked kind of close.
Like how close? Can we look at what Wolfram Alpha, get close and then go
2.
there?
I'll tell you where to start. Start at 2.
Okay.
Okay?
So it doesn't work with the other equation, like what we normally use when we can't factor it. I forgot the name of it.
When you can't the like rational zero test, where you come up with a list of candidates and do your synthetic division and all that? Yeah, that's not going to work. Because the answer is not rational.
Oh, see.
Yeah. Oh, wow, I went over. I'm sorry. So that is I'm going to say that for now, that's your only homework. Look over the test that I gave back to you. If you have any questions, we can talk about that. I will expect after the next class that you actually go tackle some of these optimization problems in the homework. I haven't done the homework videos for this
Let's make
section.
sure I clarified